All right, so in this video, we are continuing our derivation of the C6h character table. And what we did in the last video was we showed how we could break up this pseudo-irreducible representation of E1u into components using an imaginary or complex function, x plus iy. E1u originally, when it had a dimensionality 2, transformed as x and y transformed together. So x plus iy gives you one component. And we want to do this, right, because we're trying to get all of these Mulliken symbol irreducible representations to be broken up so that we have 10 or 12 rather ones down this column. So we have 12 irreducible representations, and 1 squared plus 1 squared, sum of the squares of the dimensionality equals 12, which is equal to the order of the point group and also the number of classes in the point group, so that we satisfy our character table rules. And so what I'm going to do is just remind us what we did here. We derived this one, right? And what's nice is we can use a trick that we did earlier in deriving some of these. Now we can take these individual components and actually multiply all of them by AU. And if we do that, what ends up happening is that we get back a new function. We can predict what that function would be. It would be x z, y, z. So our hypothesis here is that if we multiply AU by E1U, we should get what transforms as x, z, y, z, right? Because we're multiplying z times x and y. And so we should get E1G broken up. And so let's see if that ends up working. And so what we're going to do is we know that AU is ones across the board for the first six classes. So all of these values are going to be the same for the first 6 classes. This is the 6th one, so we just copy all these over. And then for the remaining 6, we have to multiply by -1, so we just take the negatives of them. -1s here, negative epsilon, negative of the complex conjugate of epsilon, positive complex conjugate of epsilon and epsilon. And so that is going to work pretty nicely. So then we can cross out E1G. We derive this. And you can check if you add these together, right? Here you got a 2. And previously we had a 2. And here we had a -1 plus -1. We got a -2. You could do it with the complex conjugate ones as well, and that would all work. So we're going to continue this strategy of using these one-dimensional representations to try to back out what the broken up components are. And so, and we can use the Garadas and Ungaradas to help us. And so, for example, if you think about a G times a U, remember that's respect with inversion. A G times a U is always going to give you a U. A U times a U is going to give you a G. Because anti-symmetric with respect to inversion times anti-symmetric with respect to inversion, so 2 negatives gives you a positive. So that's why these Mulliken symbols with inversions are actually pretty useful. And so we can think about, like, if we're trying to form E2U, for example, we're going to want a G times a U. And so if we're trying to form this from E1U, we're going to want to times it by a one-dimensional Mulliken symbol with a G. And so our options are AG, but we know that that's just going to get us back to E1U. And the only other option is BG. So that's what we're going to try here. We're going to multiply BG. And so just for clarity here, I'm going to highlight BG. And if you look at BG here, it's a nice pattern. It's 1, -1, 1, -1, 1, -1, 1, -1, 1, -1, 1, -1. So it just repeats there. And we're multiplying it. Our idea is to multiply it by E1U. And so if we do that, we just have to take the E1U components and every other time negative them, make them a negative one another. So in the beginning, they stay the same because we have a 1, and then we got to go negative of one another. So negative epsilon complex conjugate. Here we leave it alone. Here we go positive 1. So this is under C2. We can check here. We got a 1 + 1 = 2, so we're matching. So we're either getting E2G or E2U, but we know from our inversion logic that we went with the Mulliken symbols, that's going to be E2U. And so that was a -1. Now we're back to 1, so we just copy from the E1U. And then we're at -1. And then we're at 1. This is we have a 1 here. Sorry, I copied it wrong. I gotta be careful. I copied it from EG. I knew that it had to be a U, right? That's why I hesitated. So yeah, it's a lot of just like aligning your eyes to get correctly in line here. But here we have to be negatives. Here we remain positive. Here we're negative. These are good ones to check quickly to make sure you do it right. -2 here, we got a -2 there. So that's good. And then these ones have to be left alone. And then the last one is a -1. And so those switch from up there. And so very quickly we derived E1U. Very quickly we derive, sorry, not E1U, E2U. And so we already had E1U. So this was basically saying that, just for clarity, BG times E1U gave us E2U. And so the next logical step is to try multiplying something by BU. So if we did BU times E1U, what do we get? That's one possibility. Or we could try BU times, we're trying to get E2G, we could try times E2U. And sort of unclear what to do at this point, but perhaps we can be even more smart about this. So I'm going to cross out E2U because we correctly got that one. Let's look at the functions from which they derive, right? This is x, y, z, and zx squared minus zy squared. We figured that out earlier. We're trying to get something that is E2G, which transforms as just xy and x squared minus y squared. So what that's saying is to get from E2G, we can multiply by z to get E2U. So we want to go the other way. That's actually how we derived this in the first place when we were aggregating these earlier in the video with these real functions. If we want to go the other way, we just need to divide, right?